Dear students, today I am going to explain open circuit test and short circuit test on single phase transformer calculations. So in this experiment, we are going to conduct open circuit test and short circuit test on single phase transformer. So from the test readings, we are going to obtain the equivalent circuit. So the tests are going to be conducted to draw the equivalent circuit of a single phase transformer and to predetermine its efficiency and regulation at various loads and power factors that we are going to see in today's lab experiment. Now, coming to the nameplate details, the single phase transformer that we are using in the lab is having the nameplate details of a primary rating of 400 volts and secondary rating of 2 sets of 100 volts terminals and a capacity of 2 kVA. Now coming to the auto transformer, the auto transformer is having input rating of 230 volts, output rating of 0 to 270 volts with a capacity of 14 amps. So these are the nameplate details that we are going to use in the laboratory. Now what is the apparatus required for conducting the test? So in order to decide the apparatus, we have to fix the meter ranges in the circuit diagram. So coming to the OC test, here we are using single phase AC supply. The single phase AC supply. So single phase AC supply we are getting as 230 volts. The rated supply voltage, single phase standard AC voltage is 230 volts and it is of 50 Hz frequency. Now coming to the fuse. So fuse will be decided based upon the maximum current that we are going to allow into the circuit. So first find out the currents and then we'll go for the fuse rating. Next, auto transformer. Auto transformer is having a 230 volts input and 0 to 270 volts output with 14 amps capacity. Now coming to the voltmeter, under OC test, as it is OC test, we are going to apply rated voltage. We are going to apply rated voltage under OC test. So what we are going to do is, first we need to write the transformer nameplate. So here we are using LV and we are using HV winding on the secondary side, LV on the primary, and we are having 2 kVA transformer. Out of this 2 kVA, we are only using half capacity. So we are using a 1 kVA transformer, and as the capacity is half, the voltage ratings will also become half. That is here 200 and this is 100. So one winding is going to have 100 volts and the second winding is going to have 200 volts. So LV is connected on the primary side, so this is 100 volts winding, and HV is connected on the secondary side, so this is 200 volts winding. Now coming to the voltmeter. So as in this test, we need to apply rated voltage. So we need to apply here 100 volts. So in order to measure that 100 volts, the voltmeter that we need to use is going to have the range of 0 to 150 volts. And as it is used under AC supply, the meter type is MI type. Next, coming to the ammeter, here the current is not given the name details. So we need to find out the current. I equal to S by B. So it is 1000 by 100. So we are going to get 10 amps, but it is full load current. But the OC test is conducted under no load conditions. The no load current of the transformer is around 5% of the full load current. Therefore, I no load equal to 5% of I. which is around we are going to get 0.5. So I am using 0 to 1 amp for the ammeter. It is of MI type. Now coming to the wattmeter, as the wattmeter measures real power, we need to specify the voltage rating, current rating and power factor for the wattmeter. So here the voltmeter is 150, so the voltage range we can use as 150 volts, and the current specification is 1 amp, and as it is operating under low power factor, the power factor will be less than 0.5 for the transformer. Now at these operating conditions, we are having two types of wattmeters in our lab. One is LPF meter, another one is UPF meter. LPF meter is going to operate at 0.2 power factor, and UPF meter is operating at unity power factor, that is 1. Now, as under OC test, the power factor will be less than 0.5. We can use 0.2 power factor meter for measuring the power in this OC test. So, we need to use LPF meter. Okay. Now, as the maximum current is 1 amp, the fuse rating is 1 amp. But in our lab, we are not having any 1 amp fuse. So, the minimum fuse is 2 amps. So, I'm using 2 amps fuse here. 2 amps fuse. Okay. Now, after fixing these meter ranges, I'm writing the operators here. Ammeter is 0 to 1 amp. MI type, 1 number we require. This is the quantity. Next, voltmeter, 0 to 150 volts, 1 number. Wattmeter, 150 volts, 1 amp, LPF. Okay, this is also 1 number required. Now coming to the SC test. So single phase AC supply is 230 volts, 50 hertz, and here the auto transformer is 230 input, 0 to 270 volts output, and 14 amps. Now we are connecting HV side as a primary and LV side as a secondary. It is 1 kVA. This is 200 volts. This is 100 volts. Now under SC test, we need to apply reduced voltage by varying the auto transformer such that rated current is going to flow. So the rated current should flow here. The rated current is given by I equal to S by V, which is equal to 1000 by 200, that is 5. So the ammeter that we have to use 5 amps meter. Next, the voltmeter, here we need to apply reduced voltage, not the rated voltage. So in order to get the rated current under such conditions, the voltage that I have to apply to the transformer is around 15% or less than that. So out of 200, the 15% is 30 volts. So we can use a 0 to 30 volts voltmeter, and it is of MI type. So ammeter is also 0 to 5 amps ammeter. Now we can use 30 volts, 5 amps UPF meter. Under such conditions, the transformer is going to operate with a power factor near to 1. So I am using a unity power factor meter. So this is how we are going to set the meter ranges. So ammeter range that we have used is 0 to 5 amps. This is one quantity. Voltmeter is 0 to 30 volts, 1 number. Wattmeter is 30 volts, 5 amps, UPF. So this is also 1 number. So these are the equipment, that is meters required in addition to the transformer and auto transformer. Now with that arranged meters, you can make the connections as given in this circuit, and as for the procedure, if you connect the test, you will get the readings. The procedure, how we are going to connect the test, has been explained in another video. Now in this video, I am explaining the calculations. So The readings that we are going to get from the OC test and SC test need to be noted in this table. So here, this is OC test. So serial number 1. So here, under OC test, we are going to apply rated voltage. That is primary rated voltage of transformer 100 we have taken. So that 100 volts we are going to apply here. Now, the current that we got under OC test is 0.86 amps and wattmeter reading as 40 watts. Now, if we calculate cos phi naught, we are going to get W naught is 40 divided by 100 into 0.86. So we are going to get 0.465. 0.465 as the no load power factor. Now from the SC test, the rated current we need to apply, that is 5 amps. Now when the 5 amps current is applied, the voltage will be around 12 volts and wattmeter reading that we are going to get will be around 50 watts. Now if we calculate the cos phi SC, it will be 50 divided by 12 into 5, 60, 0.833, 0.833 that we are going to get. Now, from these calculations, if we calculate, so we need to obtain, so from these readings, we need to apply the, obtain the equivalent circuit parameters, and then we need to find out the performance of the machine. That is efficiency and regulation we need to calculate. Now, coming to the OC test and SC test data, from these two test data, we can get the equivalent circuit parameters R0, X0, R01, X01. Now, let's see how to calculate these parameters. So, from OC test, we can calculate the R0 and X0 values. For calculating the R0 and X0, let's take the OC test data. So, cos phi naught we got as 0.465. 0.465. Therefore, phi naught will be equal to 0.465 cos inverse. Cos inverse of 0.465 is 62.289. Okay, so 62.289. Now sine will be, sine of that value is 0.885. 0.885 that we got sine phi naught. Now IW will be I naught into cos phi naught. I naught is 0.86 that we got from the experiment, and cos phi naught is 0.465 that we have calculated. Therefore, IW will be 0.86 into 0.465. It will be equal to 0.399. Now, I mu will be I naught into sine phi naught, 0.86 into sine phi naught we got as 0.885. So it will be 0.86 into 0.885, 0.7611. Now, if I calculate R naught, V naught is 100 divided by IW is 0.399. So it will give 100 divided by 0.399. So we are going to get 250.62. 250.62 ohm, and X naught will be 100 divided by 0.7611. 100 divided by 0.7611, 131.388. Now from the SC test, WSC by ISC square. WSC we got as 50, ISC 5, so 5 square. 50 by 5 square, it is 2 ohms, 50 by 25. Next, R02. So as we have conducted the SC test on the secondary side, so the RSC and ZSC represent the R02 and Z02. VSC is 12, ISC is 5, so 12 by 5 is 2.4 ohms. Now X02 equal to square root of Z02, 2.4 square minus 2 square. So we are going to get 2.4 square minus 4 equal to whole under root 1.32. Let's check once again. 2.4 square, 5.76 minus 4. Yeah, 2 square is 4, so 1.76. Root of 1.76 is 1.3266. 1.3266 ohms. Now we need to convert R02 and X02 onto the primary side. So as the equivalent circuit is drawn with respect to the primary side, if you want to convert, then you have to divide with K square. So K is given by the turns ratio, so transformation ratio, V2 by V1. So 200 divided by 100, we are going to get 2 transformation ratio. So R02 equal to 2 by 2 square is equal to 1 by 2, that is 0.5 ohms. And X01 equal to X02 is 1.3266 divided by 2 square, that is 4. 1.3266 divided by 4, 0.3316, 0.3316 ohms. Okay. So we have obtained the R0, X0, R02, R01, X01. Now we can represent these values in the diagram, equivalent circuit. So let's represent. So here R0 is we got as 250.62. And X0 is 131.388. And R01 as 0.5 ohm. X01 as 0.3316. Now the equivalent circuit is completed. Now we need